This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Notes, but they will be mailed, and they are on the KLB portal as well. Okay. So do take notes down, because I think you might find that to be a useful exercise. Okay. Just trying to figure out, make sure this attaches and stays attached. Right. How many of you are here for the Unit 3? So you've got a general idea of what I do. This is what I plan to do with you today in the 1.5 hours we have. And the notes, please do use them. The examples in there I've collected are from VCE papers over the last 10 years. And I've picked out examples that I think are relevant, most relevant for this year. Okay? I can't take this off. I can't tell you that I'm an assessor. That's off the record. I'm not supposed to tell you, but I have assessed the last 14 years. That is possible. So what's happening this year, you can guess. I'll return this off. But I think I'm not silly enough to put my hand up for examiner or anything like that. So looking at what we can do in this course, we've got examples of past questions. I'll go through marking criteria. Please do take notes. There's lots of space in those papers to write notes down. If you don't have the notes, please take them down on some sort of paper. Your exam is 2 hours, 30 minutes long, 15 minutes reading time. In that reading time, you can't do anything except read and think. Okay, so no calculators, no writing of any kind. The stack is supposed to be 40%, including your wonderfully favorite ETIs. The total marks are 130. How are they broken up is on this page. Now I've handed out my last copy, otherwise I'll zoom in here and show you. But I hope you can see this anyway. There are 20 marks for multiple choice, and there are 18 other questions. But those other questions have got multiple parts. And because they've got multiple parts, you can't really tell how many questions overall there are. Okay, and be careful with those multiple parts, because some of those are worth 1 mark, some are worth 5 marks. 110 marks all up, total 130 marks. Okay. What I have done for you is make a checklist of what's in the VCE course. I've taken the dot points of the study design and put them into a checklist. So as you get ready for the final exam, keep ticking that off. If any of those don't make sense, you want to explore today, I can do that. Or if you want to talk to your teachers, we can, you can see them as well when you come back next term. To give you an idea, on waves, you've got all these topics, including standing waves, diffraction, resonance, Doppler effect, and so on. On the topic of light as a wave. So the topic is basically 4 plus a bit. The 4 main headings are the wave-like properties of light, the particle-like properties of light, then the wave-like properties of particles, and particle-like properties of particles. That's 4 main headings. But along with that, you can talk about things like what's the evidence for each of them? What is the evidence which does not support each of them? And you can make up all the questions there are in Unit 4. Okay, so keep an idea about the concepts we are studying. Light is an EM wave. These are the topics straight out of the study design. So I'm not going to go through them. They're there for your record. If any of them bothers you, we can discuss them in more detail. Being physics is very interactive. You're welcome to interrupt and talk at any time. To each other or to me. Doesn't bother me. Right. Sorry. The behavior of light as light, the behavior of light as particles, the behavior of matter as waves. You can see that very clearly split up in the study design. The last topic here, production of light from matter, that's a qualitative description only, just like Doppler effect and polarization is supposed to be only qualitative, and Heisenberg's. But if you were to do a couple of numerical questions on that from your textbook, it will help you understand this topic a bit better. Now, the time is only 1.5 hours. I could come up with such wonderful questions, but we just don't have time. For example, if I give you a 3 milliwatt laser, how many photons are coming out per second? What would be the momentum of the 3 milliwatt laser? And it's very tiny. What should be the power of a laser that you do feel the momentum? Is it possible? And you can do those sorts of calculations. So if time permits, I'll be happy to structure some questions like this. But that's what we do in class, and it's kind of fun, because you could actually calculate what sort of a laser you need to actually move something, and it's possible. Right, so here are some concepts that you might want to explore. Number one, how do we know that light has momentum? What can it do? If something has got momentum, it should be able to knock something off. What can light knock off? It can knock off, yeah? Electrons, absolutely. It can knock off electrons in spectroscopy and the photoelectric effect. It can also spin particles. It can also spin asteroids. In fact, there's a theory that the reason asteroids are rotating is because light is spinning them. Who knows? You know, I wasn't there. But that's one of the theories. It's got enough momentum that it can do weird things. How do we know that a particle has got a wavelength? Electron diffraction. Why does an oscillating particle produce light? I mean, we will explore that a little bit more today. But a moving charge simply produces an electric field. A stationary charge produces an electrostatic field. It's only when you have a charge that accelerates or decelerates that you get light. And that's Maxwell's laws in very simple English. What are standing waves? Where can you find them? You can certainly find them in strings and pipes. What about electrons? When can electrons take up properties of standing waves? Under what conditions? And those are the particles or the electrons around the nucleus in orbit that have set up a standing wave. How do we know that? And that was the Bohr model that suggested that. It was a model. It suggested that electrons can set up standing wave. And Schrödinger went on to calculate the equation for the standing wave for the 1s1 hydrogen electron. Nobody has ever done any other calculation since. And that was 1924. No changes since then. Why can electrons diffract? We answered that in the previous session. I would love to diffract. You know, multiple personalities. Now, same personalities, multiple places. It's absolute bizarre, but why can't we? And if you look at the equations of diffraction, or the equations of momentum and wavelength is h over momentum. H is this quantity which is 10 to the minus 34. So in order to try and get a momentum of 1, you need to have an mv, mass times speed, of about 10 to the minus 34. Or at least a number that is realistic. We can't do that. We can't travel at 10 to the minus 31 meters per second in a uniform way for extended periods of time to diffract. So I think these are very relevant questions that should and could be asked in the VCE exam this year. Let's have a look. Is light a transverse or a longitudinal wave? I hope you know the difference of that. Light is one of those things which is transverse, just like a boat which is bobbing up and down in the ocean. The waves are going under it. Light does something similar. Why does the sun emit light? What is going on there? That's the acceleration and deceleration of charges. It's a massive fusion generator producing lots of plasma. And you know what's going to happen? The sun is going to go big and eventually burst. That's why, as a physics student, you should never call anybody a star. Because you know what a star is. It's full of gas. It's going to explode one day. You don't want to call your favorite person a star. Supernova maybe, but star now. So why does the sun emit light? It's got this massive amount of plasma, charged particles flying apart, gravity pulling it together. That's what's going on. And it's the acceleration and deceleration of charges which causes that. What about the electromagnetic spectrum? You should have a rough idea. Visible light is roughly 450 to 650 nanometers. Red is about 650. Well, it's about 750. 400 to 750. Okay. Red is about 650. The red laser is about 650 nanometers. Your green laser is about 500 nanometers, which no school should have because it's banned, I think. But yeah, most schools do. But that's the green laser. Looking at what is important here is the fact that as you go towards the gamma rays, the wavelength becomes very small, the frequency becomes very large, and the energy becomes very large. So you know the relationship there. We're going to put a few equations up here, which you should be scribbling down, just as a backup. So we write down some properties of photons, and we write down some properties of electrons and particles, for example. So we know for the case of a photon, E is Hf, is Hc over lambda, and the fact that H has got two numbers, or 4.14. I'm very familiar, this is an arts building, and first thing tomorrow morning there's probably going to be an art lecture in here, and you're going to think that's a piece of art. But I think it's good to put those things there and leave it there for them to contemplate. So when you look at the energy of an electron, it's a very different thing. The energy of an electron can be gained by accelerating under a velocity, under a voltage gradient. You can pick up the energy of an electron by dropping it from a height, gravitational energy, kinetic energy. All of those energies are possible. Half mv squared kinetic energy can be gained by taking the electron, charge of the electron, and accelerating them through a voltage. Where can you do that? You can do that in an electron gun, which looks a bit like that. Something like that, put it through a vacuum tube, with a high voltage through it, and you have an electron gun. If you put a hole at the other end, the electrons will come out. If, however, you decide to put a massive target over here, and the electrons hit that target, can you do it like that? No. Like that is better, something like that. So the electrons hit this target, you're going to get X-rays coming out. And there's your X-ray tube. And when we get to that point, we'll talk about some equations relevant to that. Next slide. I wanted to show you how moving charges can produce light. Looking back at this slide, light is this oscillating movement of electric and magnetic field. An oscillating, changing electric field creates a magnetic field, creates an electric field, and that rate of creation is the speed of light. Okay, that was calculated by Graham, Clark, Maxwell, and others around 1860s, and we're still trying to verify how they did that. But that 1860s theoretical calculation got them to 3 times 10 to the 8 meters per second. So let me show you this particular, I think I downloaded it correctly here, and there it is. If you just start that, moving, linear. Okay, this is a moving charge, just like a current, and it has with it an electric field. And you can see what the electric field is doing. And I can increase that speed. But the moment I try to move that in a sinusoidal or circular manner, the electric field begins to oscillate as well. That then produces a magnetic field, which then produces light. So you need an accelerating or decelerating charges to see that. You can play around with this, kind of fun. Okay, all that stuff. So coming back to where we were, we don't need that. Here we are. Okay. One of the mundane things about this course, and it's very significant, but just the fact that it's very simplistic, we tend to overlook it, is Snell's law and refraction. The fact that light refracts. Do particles refract? So if I throw a piece of stone into water, does it bend its direction? Have a look next time, and you'll actually find it does. It slows down. As it slows down, you might find that it changes its direction. If you drop it vertically down, it goes straight down. So next time you take a little stone and throw it into a Yarra River, you won't see it, but that's Yarra River. In a swimming pool, you see it bend. You'll actually see it bend, okay? And you guys are doing chemistry, right? You got the periodic table in that river. It's a huge resource, you don't know about it. No, it's a fantastic river. But looking at Snell's law, why do you have a refractive index? What does it mean? It's the ratio of the speed of light in air, divided by the speed of light in the medium. And because the speed of light is always slower, the refractive index is always going to be greater than 1. Okay, light can slow down going from air to another medium, can't speed up. Therefore, the refractive index is greater than 1. If you go from an optically denser medium to an optically lighter medium, you can have this unique phenomenon called total internal reflection. And the angle at which it begins to take off is called the critical angle. You don't have to go any further than looking at this equation. N1 sine theta 1 is N2 sine theta 2. And you can look at sine theta 2 as critical angle, and you'll realize that the critical angle is in fact sine inverse 1 over the refractive index. Good to draw a diagram, good to make things clear of what the optically dense and the optically lighter medium is. When you draw these diagrams about rays, please make sure you do put an arrow there to say it is a ray. And what are these rays? We're talking about light as a wave, and suddenly we have a ray. What is it? So once again, if you want to draw a fancy diagram to explain that, here's the light, wave fronts coming like that. I look at the tangent at each point here, or I just connect that sort of tangents here, and that's the ray. So I'm going to draw tangents parallel to each other, and the point which connects that is the ray. Okay? So a ray diagram is basically a wave diagram drawn in a simplistic manner. This is a fiber optic cable. The core, the cladding, and the jacket. The core here is a glass of higher refractive index, optical glass, and the cladding is a lower refractive index, something like magnesium difluoride. And as a result of that, light can be trapped inside here. And that's what's happening with fiber optic cables. Why do we use fiber optics rather than copper? That has to do with the fact that copper, you have a problem with high frequencies. All the signal goes on the outside of the copper, and a large part of the copper is wasted. Okay, so we use fiber optic cables in the NBN. Okay, next. Here's a question, 2017 exam paper. And you can see here, one of the questions says, sketch the ray or rays that should be observed. Less than the critical angle. One ray will come back, and part of the ray will refract. Not everything refracts in a light beam. So if I reverse this question and said, here's a light beam entering the surface, you might find that part of the light beam is reflected, and part of it is refracted. Both will happen. Okay? And that's why I wanted to put it up there. The question. Explain why the observer cannot see the laser. I like this new trend, or maybe I don't. It keeps talking about not factors. Explain why this theory does not support this evidence. Why the observer cannot see the laser rather than when can the observer see the laser. But this question is a little bit trickier to answer. Why can't this person see the laser? Okay? And you have to answer in some ways in a positive sense because you're physics people, you like to be positive. But I know you have to make sure you answer that question as well. How do you go about it? Three things. Firstly, you must absolutely make sure that you've got some significant and correct science in there. Something which says to the examiner, I've understood what is it you're asking. You see the laser when light falls on your eyes, or something to that effect. And you're getting total internal reflection, therefore no light is getting to you, therefore you don't see it. I know it's very prescriptive, but that's one of the ways to answer these questions, okay? Dispersion is this phenomena where light, different color light bends different ways. When Newton saw this happening, for the first time he reckons, he said spectre, ghost. You know? Those who do in Latin will understand that spectre means ghost. So where did this come from? And hence the word spectrum came out of there. Well, why does it split up into different colors? Why is the red bending the least? Answer, the red has got the lowest refractive index. You can keep going with questions. So why does it have the lowest refractive index? Because it's traveling the slowest. Why is it traveling the slowest? That's got to do with the way the electromagnetic field of red light behave compared to the blue light. So somewhere you have to draw the line. At the very least you can say the refractive index of red is different to the blue. Okay. What quantities stay the same as light travels to different medium? So if you start off with a certain frequency for red, that's not going to change. The wavelength and the speed changes. All right, Doppler effect. Very qualitative description only. If something approaches you, the waves can get compressed. You can picture that. The wavelength reduces, the frequency goes up. As something goes away, you see a rarefied front behind you. So the wavelength has gone bigger, the frequency has gone down, and therefore you hear two different sounds. There are lots of applications of that. If you really want to hear this, I wouldn't suggest doing this, but you could. I mean, you could go on a bike with a little bag and say bomb, 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 just run down, and you see these police sirens from everywhere. Beautiful effect, the Doppler effect. Please don't do that. Nasty thing to do. But you can watch it on the internet. Somebody's tried that. So what I'm going to show you is a description which I showed the previous talk, and I hadn't planned to, but I just did. So here we go. Let's try that.
The observer.
Sorry, I'll just
Yes.
go a little bit back.
It's the apparent.
I think what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay, that's enough for it, I think. But you get the idea. That's the sort of thing that's happening. And it's very easy to demonstrate. One of the tools we have in our lab is a really big ruler, a meter-long ruler, and in that we have 1,000 hertz, and we spin it. So as you spin it, you can hear the sound changing. Yeah, a very clear demonstration. You can try that at home. It's not hard to do. Okay, the properties of waves that you could be tested on. One thing that I'm a bit wary about, at least in some of the students I have, is the superposition of waves. And I think we have not spent a lot of time talking about it in schools. Light can be traveling, standing, longitudinal, or transverse. No, light can't be longitudinal. Light is transverse. But you can have waves that are longitudinal or transverse. The two extremes of wave superposition that you see in this course are waves that are completely in phase, and when they superimpose, you get a very large amplitude. That is constructive interference. Two waves that are completely out of phase, perfectly out of phase, if they add up, you get nothing. And that is a completely destructive phenomenon. That's what your double slit interference and all those patterns are based on. But that's just two extremes. A lot happens in between. All right? So how do you calculate that? So you could draw two waves, and you may actually have to calculate what is the resultant. So you could have a wave like that, and you could have another wave that you're adding onto it that could be doing something like this. So what's the resultant of those two waves? How do you determine that? And one way to do that is to add up the magnitudes of those waves at different points. So simply add them up. So over here, this wave's resultant is up here. This is over here. This is down here. And you can sort of see what the resultant wave is going to look like, okay? And whatever the resultant comes out to be. And I've shown you an example on the right here of a particular addition of waves that I find fascinating. And I hope you can see that. Here's a wave. Here's the other one, which is about the same amplitude, but slightly different wavelength. Very, very slightly different wavelength. By the way, what's the amplitude here? It's from the baseline to the top, not from the bottom to the top. And if you did that, you see these oscillations of sounds. And I would love to show you that animation as well, and that sound as well. It's called beats, and you can hear that in concert sometimes. So that's what beats are, and that's what constructive and destructive interference is as well. Remember, in constructive interference, the path difference is n lambda. Destructive is n minus half lambda, and is an integer. Why is that important? Who cares? That's what diffraction is based on. And anybody who's going to do engineering, medicine, sciences will appreciate how important diffraction is. Whether it's electron diffraction to study crystal structure, X-ray diffraction, the entire area of diffraction employs tens of thousands of people and is worth multi-billion dollars. So I'm glad you're doing it in year 12. I wish I had. It's a phenomenal thing to learn. But it's based around this idea of constructive and destructive interference. Here's an example of standing waves in strings. Of course you can create standing waves in anything. If you have the right frequency, if I put the right frequency on this table, this whole table can begin to oscillate and break apart. Bridges can break, have broken. Yeah? These things do happen. So if you set up the oscillation as the same magnitude as the fundamental frequency, you're going to get massive oscillations in the middle, and that can cause things to break. So if you have a string that's fixed at both ends or a string that's loose at one end, you can set up these things called harmonics. They're called harmonics because they produce music in harmony. That's where the word harmony comes from. And the fact that you can produce that is because the tone is pure. You get a single frequency which is loud and clear, the fundamental being the clearest. So when you're playing a guitar string, for example, you change the length. What you're plucking is setting up the fundamental tones. Okay? It is a unique combination of speed, L, and frequency that creates these harmonics. In a string closed at both ends, you will get all the harmonics. Whereas a string open at one end, you will get only even harmonics, odd harmonics, first, third, fifth, and seventh. Those guys are doing music theory. Anybody here? So you know that the third harmonic would be the second overtone. Okay? But we don't have overtones here, but you know how the octave scale is set up here. I can show you a demonstration really quickly here. Here it is.
It's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. I have what's called a standing wave. That is,
these points here don't move. That's why it's called standing.
Reflects,
that's a node. That's an antinode.
Constructively interferes.
I'm not going to waste your time with all this.
So here we have a jump. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic.
You can watch this later. I just want to show you what it has. Any questions on this? All right, I have a question for you. I think I won't touch this. It's very easy. but there was another question I had up here, this one here. There are two successive harmonics in a string at 625 and 875 hertz. They're successive. Has this been produced in a string closed at both ends or a string open at one end? How do you know that? What is the fundamental? And what will be the ninth harmonic? How would you go about solving that? So numbers are 625 hertz and 875 hertz. If I say this is a string closed at both ends, then I can produce all the harmonics. That doesn't seem to make sense because 625 and 875 is not going to give me the right answers. I know the answer is 125 hertz as the fundamental. How would I get that? But how would I know it's 125? You can find the difference between them, possibly. Yes, and then that difference is the fundamental. Yeah. You can look at the highest common factor, and that will tell you what the fundamental is. If I want to know the ninth harmonic, what will that be? Now you can go about saying it's going to be 9 times the fundamental. That's all. The ninth harmonic will be 9 times the fundamental. The third harmonic will be a third times the fundamental, by definition. So 9 times 125 hertz. Okay? I think this is an interesting question. How long would the string need to be? So once you work out the frequency, you can then say it's NV over 4L, and you can work out the rest from there. So this should be equal to NV over 4L, and knowing V, you can work out the length. Okay? It's the ninth harmonic. So N is 9. Any questions so far? Okay. Going into diffraction, it's Young's experiment. The work of Young was a quite mathematical bit of work. One of the things he said was that for small angles, sine theta equal to tan theta. In fact, his original work was simply called sine theta, tan theta approximation of diffraction. It wasn't called Young's double-slit interference. And I'm going to draw a quick diagram here to show you the sort of mathematics he was looking at. Oh well. I can't do it as nicely as the art students would, but we'll have a look. So if this is L, and you're producing the central maxima here, and then you've got different maximas at the other end. So I can say this is the central maxima, n equal to 1, n equal to 2, n equal to 3, like that, right? And these are your antinodes. In between them will be the nodes. If I want to call this distance from here to here x to tell you how far it is from the central maxima, and I connect this up with two lines, draw a 90-degree line here, this extra distance traveled is the path difference. This is d. This angle is also theta, so is this, so is this. In fact, if I was to connect it from the center here, because L is so far away, this angle is also theta. Yeah? So the assumption here is that L is much, much greater than D. Now I can apply right angle geometry. To this triangle, I can say sine theta is path difference over D. To this large triangle, I can say tan theta is equal to x on L. And if I put the two together, I get path difference over D is equal to x on L. That's Young's experiment. Okay, then if you assume that you're talking about constructive interference, you can say it's n lambda on D. There it is. Most of the questions based on diffraction are around this mathematics. For example, what happens to the spread if wavelength increases? So you can see from here, if all else is the same, if you increase the wavelength, you're going to increase x. If you increase L, you increase x. If you increase D, you reduce x, etc. The delta x quantity that we talk about is called the fringe spacing. Okay, the fringe spacing delta x is this distance from here to here. In a double slit interference, and only in a double slit interference, is that delta x constant. All right? If you have 1 or 3 or 4 or anything else, these distances change. They're not equal. Only in double slit they are. And in that particular case, this delta x here will be L lambda on D, also derived from here. Okay? If you take n equal to 1, you will get that answer. So these are the equations that you see here. Now, this was a question from 2017. I won't run through the whole mathematics of that. It's in your notes. but I can show you the general gist of it. The two sources, the D value is 4.0, the L value is 24. So yes, it's not as big as you might see in light. For example, L will be in meters and D will be in nanometers, but still, L is much bigger than D. What the values will tell you is the distance between person 4 and person 2 is one wavelength. This is half a wavelength from here to here, which means that this person at position 3 will hear soft sounds and the person at position 2 will hear bright sounds, okay, or loud sounds. So this idea about constructive interference, destructive interference, path difference being equal to n lambda or half a lambda, etc., is what these questions are based on. Here's a complete calculation and description of that, and I think you can solve this at your own time. I'll just put it there in case we have time, you want to explore any of these, I'm happy to do that. Otherwise, I think you are clever enough to follow this on your own. Now, I wanted to show you these images of single, double, triple, multi-slits and gratings. What happens? If you take a single slit diffraction pattern, very large central maxima and very low other antinodes. Double slit, everything is equally spaced. Double slit, all fringes are equally wide and equally apart. Three slits, that's not the case, but the pattern becomes sharper and sharper. If you take a grating just means thousands of these slits per centimeter. 10,000 lines per inch is a standard diffraction grating you get from the United States that we have. 10,000, imagine that. Right? You get very sharp lines at very sharp points. All right? So that's what the difference becomes. So that grating becomes more similar to what a crystal might be behaving like. So if you take a light source like X-ray and you pass it through a crystal, the gap between atoms is a few angstroms. Angstrom is 10 to the minus 10 of a meter. All right? And if you have a wavelength of about that or just bigger than that, you will see diffraction images beautifully. All right? That's the whole idea behind diffraction, from which you can calculate interatomic distances. Once you know interatomic distances, you can produce the crystal structure for that particular element. If you think I'm just talking and it's beyond you guys, it's not. I'm not bragging here, but I'm going to show you that we have a group at Scotch, year 11 students, who are doing X-ray diffraction, X-ray crystallography as an extension project, and have discovered a new crystal. And they're now looking at the full diffraction pattern using the X-ray instruments here at Melbourne. Good luck. Well done. Let's say I give you this image, and you are the exam writers, and I ask you, produce some questions on this. What will you come up with? This diagram is from past VCE paper, and later on in this presentation I'll show you some of those things. But here you are, it's a laser, double slits, and you can see the central maxima in the middle here, and then you got the first order dark, the first order bright, the second order dark, second order bright, and so on. Okay? So this position X is n equal to 2 destructive interference. And I tell you that this path difference is 750 nanometers. So write that down. So the path difference is equal to 750 nanometers, right? And I also tell you that n is equal to 2, and it's a node. So it's dark, in case you're not clear. That's what a node is. What can we calculate from here? So if I know the path difference is this, and equal to 2, then I know that this must be equal to 1.5 times the wavelength, from which I can calculate the wavelength. Yes? If I tell you what the wavelength is, and you repeat this experiment, you should then be able to calculate the speed of light, but that's a different question. So calculate the wavelength of laser use. What is the path difference point X? You can do that. What happens now if all these quantities are changed? You go back to this equation, and you look at the questions there, and find the answers buried in here mathematically. That's a useful expression to have. All right. Diffraction using white light. What's the difference? The central maxima will still be white because the path difference is 0. But when you get to other points, you find that the red is at the bottom. Why? Because red diffracts the most. This is in opposite to what you had for dispersion. In dispersion, red bent the least. Here, red is bending the most. It's not bending. This is diffraction. It spreads the most. And that's why red is down here and violet on top. Photoelectric effect, how are we going for time? Okay, good. We have till 3, right? If it looks like I'm getting too close or running out of time, please let me know, because you have to go to the English talk after this, right? By the way, congratulations on being selected for KLD program. I think it's awesome. You get to see Melbourne Uni and, you know, some nice lunch. So here's the diagram for electric current and voltmeter reading. You've seen this diagram, you've seen these graphs. Now, I think Melbourne Uni has done a tremendous program here for you guys. Please make sure you say thanks to Michaela. What does this 1.85 mean? What is the significance of that? This is the voltage that was needed to push back all the electrons. Let's trace this graph very quickly. In this cell, if you apply this voltage and the voltage is 0, some of the electrons make it to the other end. They've got enough energy to make it to the other end. But if you start reversing the voltage and make it negative, you start pushing electrons back. The one electron that has got the most energy will be the hardest to push back, and that is 1.85. That electron has an energy of 1.85 EVs. That voltage there equates to EVs. So when we talk about charge of an electron, energy Q times V, if you replace the charge Q sub E as E, electron, V, EV, that's where the EV is coming from. It's the energy needed to push an electron, or the energy gained by an electron as it goes through 1 volt, acceleration. That's the energy it gets, EVs. So that produces the EV values, okay? What happens if you increase the frequency? What happens if you increase the intensity? I think you know that very well. Just make sure this line here, straight line, saturation current, doesn't extend straight all the way. I've seen that so many times. Not true. Once the voltage is negative, you're not going to get saturation current. Okay? So this graph here is produced by looking at these values of 1.85. If you keep changing the frequency, you will keep getting different values of stopping voltage. You take those stopping voltages, plot them on the y-axis, put on the x-axis, you put the frequency of light you were shining, and you get 3 or 4 or 5 data points, and that's all that was used to prepare this graph. The gradient of this is h, and this, what are these quantities? This thing here is called the threshold frequency. It's the minimum frequency needed to eject an electron. This intercept on the y-axis is the work function. It's the minimum energy needed to eject an electron. The gradient is h, and this is a conservation of energy expression. Why? Because if you look at this a little bit closer, as Einstein did, and he said this is a straight line, y equal to mx plus c, and you realize this is why he got the Nobel Prize. He didn't get it for anything else. It was for the photoelectric effect. He didn't discover it, he explained it. Yeah? Let somebody else do the discovery, but if you explain it well, you get the Nobel Prize. So this was y equal to mx plus c. What's happening here? What's on the y-axis? E k max. What's n? H, x, f, minus the work function. And that work function is h times f naught. The irony was, and the interesting part was, no matter what metal we took, all the graphs came out to have the same gradient. Okay? They all had the same gradient. So these values on the y-axis were the stopping voltages. The stopping voltages here are the same as the EK max in EVs. This is the property of a particle. It's kinetic energy of a particle. This threshold frequency is a characteristic property of a wave. Particles don't have frequencies. Planck's constant was something that had been calculated by then as related to maybe a beginning of quantum physics, to try and understand that there's a packet of light, a smallest quantum of light, called a photon, and H was significant then. And this work function here, these quantities here, were well and truly established as the binding energy of electrons to a metal, to the nucleus. And here is this equation which combines the particle property with quantum physics, with Planck's constant, with work function of binding energy, and frequency of a wave. And that combined the quantum and the classical viewpoints together. All right? That's why this equation was so significant, and Einstein got the Nobel Prize for that. Any questions on this? You know why this is dashed here? Because there's no data there. If you ever have to do calculations here where the bottom half is wiped off, how do you calculate the work function? Don't forget the basic equations. The work function is h times f naught. You don't really need to extrapolate it down to the y-axis to calculate the work function. All right? If I have a graph like this one here, compare that to this. Let's put some numbers here. Let's say this is 1 and that's 7. Which one has a higher work function? 1 or 7? 7, okay? It's the magnitude we are looking at. The binding energy is not a vector quantity, it's a scalar quantity. All right. Spectroscopy. The basic physics behind spectroscopy and the photoelectric effect is not too different. Light shines on it as a photon using those energy equations. And if you bring that board down, we can do a little bit more with this. We can say for a photon, it's produced in the sun is equal to mc squared. We can write that as mc times c, which is momentum times c. And that tells us that the momentum of a photon will be energy over c. And because energy is hc over lambda, you get h over lambda. There you go. That tells you the momentum of a photon. We can now reverse this equation and say the wavelength must therefore be h over mv. And there's the momentum of a particle. And we just put a little dV here, the de Broglie's wavelength. Okay? So there's no magic in these equations. You've done special relativity, that was magic. This is not magic. Right? So that's how you can calculate the momentum. You can see the wavelength and momentum could be similar for electrons and photons. Okay? But the energy is a completely different game. So what's happening in spectroscopy? These photons come here, they collide with these electrons at the bottom, the ground level. Okay, question for you, completely different. Can you tell me 2 situations in which we get something called a population inversion? That means electrons are not in the ground state, they're at n equal to 2. When will that be? 2 things, 2 places. You know them. Number 1, the sun, very high temperatures. Okay, number 2, laser. So when you're pumping a laser, when you charge a laser, the electrons go up to a high energy level and they stay there. When you turn the laser on, you're actually turning it off. And the electrons cascade down and they come off with a uniform light. The reason you get a uniform wavelength, because usually the first excited state is fairly flat. The rest of the orbitals are highly convoluted. As a result of that, these lines that you see here become bands. You see lots of fine lines there because you got suborbitals. Along with suborbitals, you got uneven orbitals. And that's why the Bohr model collapsed. The Bohr model could only work for the 1s1 hydrogen electron. It doesn't work for anything else. Okay? Here it is. Here it is. 1913, the Bohr model was proposed. This is the Bohr model. Right here, this diagram writes it beautifully. N equal to 1, 2, 3, and finally you get the conduction band. Electrons can go from the bottom to the top. They can't come down from the conduction band to the valence band. Okay? By the way, this gap here has got different names. That 13.6, this is hydrogen. The chemists call it binding energy or ionization energy. The solid state physics people, they call it band gap. You guys call it the work function, the photoelectric effect. They're all the same thing. The only time an electron will fall back from this conduction band to valence band is in the case of an LED. Okay? These are diodes, basically. Silicon diodes of this structure. All right? Difference is this is a gas, silicon's a metal. But the physics is the same. Right. So when you look at questions like this, what would you make the questions to be? If I give you this information, if you were writing the exam, what would you say? Suggest some questions. I know there are some written out there. These are the questions VCE has asked. What is the wavelength emitted or absorbed, smallest to the largest values? Think energy. Okay? Largest wavelength, smallest energy. What is the smallest energy emitted? From n equal to 6 to 5. Yeah? What is the, you can write these down by the way, just as answers. What is the largest energy absorbed? From 0 to 13.6 and more. You can get all of them. So if I have to make a graph of those, of absorption and emission, it'll take too much time. But I can actually show you how emission and absorption spectra work really easy. What lines will be absorbed here? Energy is corresponding to these. Okay? What lines will be emitted? Corresponding to when the electron falls back. And these are your emission lines. Okay? I've got another tricky question for you. This is the hydrogen spectra. So we look at the sun and we see some lines that are missing, some dark lines. We say, because of hydrogen. There's hydrogen between the sun and earth, and the hydrogen has absorbed the energy, the electron has jumped up, and therefore we see absorption spectra. What does the electron do once it's absorbed the energy and jumped up? It doesn't stay there. It jumps back down. I missed that radiation. How quickly does it do that? Instantly. It jumps up, falls down, I missed the radiation. Then why do you see dark lines? It's absorbed the radiation, jumped up, emitted the radiation back. Why are you seeing it? Any ideas? Yeah, it's scattered in all directions. It's absorbed in one direction, but it's scattered in all directions. Exactly. That's where they got the idea for the band, you know. One direction, all directions. Never mind. So you can see the emission and absorption spectra working here is basically to do with two things. That light has got momentum. It can knock these electrons off. The electrons, on the other hand, are in these discrete. The word is discrete. Don't forget that. The electrons are in discrete orbitals. They can only exist in those things because 2 pi r equal to n lambda satisfies the criteria of a standing wave. Okay? So electrons are in the form of waves, and the photons are in the form of particles, and that's how you can explain the photoelectric effect and spectroscopy. Two evidence of the reverse happening. The light has got momentum, and electrons have got wavelength. Okay. The modification to Bohr had to be made, the Bohr model, because the Bohr model failed to explain multi-electron atoms. Schrödinger cleared some of that up, coming up with SPD and F, and then Dirac's work, of course, with the 4 quantum numbers leading to Pauli's exclusion principle and Heisenberg's uncertainty principle, all came out of this work of Schrödinger. The only equation of a standing wave ever solved was for a 1s1 hydrogen atom, hydrogen electron, nothing else. Okay. If you are at university and you want to do more than that, please send me an email. Come up and see some of the work I have done. But there's no way we're going to solve that in a hurry. So this is the work of Schrödinger and Dirac, and that's why the Bohr model failed. The existence of fine lines in many spectra couldn't be explained, and of course Heisenberg's and Siemens principles couldn't be explained either. All right, this is what diagram VCEE often expects from you. In fact, it's in the examiner's reports of a standing wave. Completely meets the circumference. These amplitudes are highly exaggerated. So we get the idea that the 2 pi r is the circumference of the circle, and it must fit in an integral multiple of wavelengths in there. What about Heisenberg's principle? The mathematics behind that is fun, it's tricky, and it's not part of the course, except the overall expression that the uncertainty in position multiplied by the uncertainty in momentum is h over 4 pi, greater than or equal to h over 4 pi. And I'm sure your physics teachers have told you about that, about the speeding guy, right? Caught by the policeman, saying you were speeding, do you know how fast you're going? He said, no, but I know where I am. You know, because if you know how fast you're going, then you wouldn't know where you are. So take what you like. So the uncertainty in momentum is very high, the uncertainty in position is very low. That's what happens in a single slit. You have identified the width of the slit. There it is. That's it. Now you dim the light so low that you only get one photon traveling at a time. Then why would it diffract? Or why would it interfere, set up a standing wave, or set up an interference pattern? There is no other to interfere with, right? Or if you have an electron beam and the electrons are only getting through one at a time, the electrons have nothing to interfere with. Why would they set up an interference pattern? It's to do with the fact that there is uncertainty in its momentum. The uncertainty in position is very small, but the uncertainty in momentum is very large. And look at the expression here. Momentum wavelength. A high uncertainty in momentum means a high uncertainty in wavelength. And a high uncertainty in wavelength means your fringe spacing or X value is also very uncertain. So where it's going to land is uncertain. Isn't that diffraction? Right? The wave is spread. And that's the basics of Heisenberg's applied to single slit. Okay, I've just stated all that in words here as well. By the way, if you want to read extra, here are some things down here that will help you understand these things better. What is meant by confinement, electron tunneling, quantum numbers, etc. All these, anybody here doing IB chemistry, IB physics? No. It is part of the IB program to some extent. Anyway, you can have a read that. Electron diffraction is one of those things that is really important in this course, and it's such an important part of physics. I still stand by the fact, I believe that the course you guys are studying in physics is the best in Australia. The Victorian course is really comprehensive, and there are some fun things like this one here. Electrons can diffract. These are particles that can diffract. Under what conditions can that happen? Well, first of all, the interatomic distances between atoms is about in the order of 10 to the minus 10 of a meter. So you want the wavelength to be in the order of 10 to the minus 11 of a meter, or 10 to the minus 9 of a meter. Anything big, any variation other than that, you're probably not going to see much diffraction effects. If it's slightly bigger, it's actually good. If it's slightly smaller, well, let me rephrase that. If you're actually doing diffraction of a crystal under an electron microscope, right, what you're going to find is if it diffracts too much, the pattern is going to spread so far that you won't get any information. You don't want a lot of diffraction. A lot of diffraction means low resolution. You actually want high resolution and low diffraction. So you'll be happy with a wavelength of 10 to the minus 11 rather than 10 to the minus 9. I think that's too hard a question for VCE, but I think it's a good one. So what do? How do you create an electron with that wavelength? And that's where some wonderful mathematics can come into play. So looking back up here, I've said that the kinetic energy of an electron is Q times V. And the kinetic energy is half mv squared. So from here, speed is equal to 2 QeV over m square root. Therefore, momentum 2 QeVm square root, and hence the wavelength is h over 2 QeVm. Simple maths. That tells you that by changing that voltage at which you're accelerating an electron, you can dial up its wavelength. So if you want a wavelength of 10 to the minus 11, 1.2 times 10 to the minus 11, you can calculate what voltage you need. And you can change that to get exactly what wavelength you need. And you can change that while you're doing your analysis. And electron diffraction changed completely the way we do crystal structures. Now, these two patterns look similar. The one on the left is by a photon, the one on the right is by an X-ray. Why do they look similar? What are these diffraction patterns? Okay, they're diffraction patterns. We won't go down that path. These rings represent all sorts of things. They are indicative of the crystal structure, how far the atoms are. It's a Fourier transform of the 3D crystal structure, if that makes sense. So what we do here, we compare those two distances, and we say they're exactly the same. Therefore, what must be same? Wavelength is same, momentum is same, the energy is not same. And that's about half a dozen VCE questions in the last few years. All right? Don't believe me, I'll show you some questions. Come in. This is an electron gun. I think I drew a bit of a diagram over there. And these equations that I've just gone through up on the board here are also listed here for you, in case you didn't copy that down. So you can determine the wavelength of an electron by dialing up the voltage under which you accelerate it. On another matter, if I apply positive voltage to an electron, I can speed it up. I can keep doing that, keep increasing the voltage till I reach gigavolts. And by then I can make the electron go at about 99.995% of the speed of light. That's called a linear accelerator. Once I've got that and I want to take it to another decimal place, I have to then go through something called an undulator and a wriggler, which helps you to move the electrons and get them the high kinetic energy. That's the synchrotron part of the energy storage devices, electron storage devices. Then you bend it. How do you bend the electrons? Using a magnetic field. Magnetic fields will bend electrons. Electric fields will accelerate them in a straight line. When you bend the electrons, they now begin to go in a circular path. But the kinetic energy hasn't changed. So their energy is not changing. But you're giving it energy. Where does it go? It comes off as synchronous light. And the synchrotron light is called synchronous because a number of things. And towards the end, we'll highlight some of these different light sources. A synchronous light is just that. It's synchronized. All the waves are in phase. They're plane polarized. And they're highly intense. 1,000,000 times brighter than the sun. Okay, that's the synchrotron that we have on Blackburn Road at Monashini. Right, any questions so far? Okay? Questions for me, from me to you guys. Just a yes or a no. Can a photon have mass? No. Can an electron have momentum? Yes. Can an electron have frequency? No. Can an electron travel at the speed of light? No. Because relativistically, it's impossible. Okay. There can be many other questions like this. There was one year, you're just being mean. You should have not done that. There was one question that said, which electron travels faster? One that's accelerated to 100 volts or one that's accelerated to 1,000 volts? Very simple question. Which one travels faster? 1,000 volts means we've got 1,000 volts of accelerating voltage, going to have a high kinetic energy, therefore higher speed. Okay, part B. You've got two photons. One is red, one is blue. Which travels faster? People struggle with that. Thank you. Same speed, the photons. As I said, it was a mean question, shouldn't have asked that. Right. Conflicting models. I mean, this bit about which model says what. Spectroscopy. Be clear in your mind what it's telling you. Spectroscopy says electrons behaving as waves are set up discrete energy levels. Light is coming in small bundles of energy called photons, quantized energy levels, quantized energy packets. Packets. Momentum. They're knocking these electrons off. What about the photoelectric effect? Photons coming as bundles of energy. Yeah, momentum. What about diffraction? You have electron diffraction showing you wave-like properties of electrons. What evidence backs which theory and does not back some theory is important. Okay? Why is the photoelectric effect not supporting the other one? And then you can talk about time delays and things like that. And I've got some notes on that as well, I think. All right, some general marking criteria. I've got a number of questions here to discuss with you as we go along. By the way, this business of quantum stuff is getting pretty exciting. Not only is quantum computing a reality now, we're discovering new quantum stuff. What does that mean? The quantum charge is an electron, right? The quantum mass is probably the Higgs boson. We don't quite have, what else would we have? Quantum charge, quantum mass. We don't have a quantum dipole. The smallest possible magnetic dipole. That's on the way. People are researching that. There is a project which has taken some superconducting nanotubes and buried them in the detectors at CERN. If you have a smartphone, just Google that. What is a superconducting nanotube? Do that now and you'll find something really interesting. These things are happening right now as we speak. Good marking criteria, or general marking criteria. This is straight from the examiner's reports on the internet, okay? I say that even in multiple choice, it's good to work things out. You make less errors, basically. The idea is about relevant and complete working. There's no point in saying something that is correct, is magnificent, but it's nothing to do with the question. You're not going to get any marks for it. So why does increasing the frequency, showing the increase in stopping voltage, not support the wave-like nature of light? And you go on to talk about how magnificently it supports the particle-like nature of light, you get a 0. You have to answer the question. So please be very careful what the question is asking. I found this, I shouldn't really call it a formula, but just for a lack of a better word, I said follow this method. Okay? In your answer or worded responses, make sure you've got some background science. Relevant, of course relevant, background science. You have somehow related it to the question. So you could have said, in this photoelectric effect experiment, increasing the frequency, increase the stopping voltage because of this. Had light been a wave, increasing the frequency, think sound. If you increase the frequency of sound, what happens? The energy doesn't change. Does it? No. The energy doesn't change. So why should the stopping voltage change? If I increase the intensity of a sound wave, I change the amplitude. I'm actually changing the energy. So if light was a wave, think sound, right? If light was a wave, increasing the intensity should increase the stopping voltage. But it does not. When you say it does not, then you're answering their question. Okay? So that's the clarity of answers that you need to develop in your worded responses. I've got a whole bunch of questions here, and depending upon time, you can go through some or all of them. I don't even remember which year this is. I think this is going back 5 or 6 years. You were given a bunch of data, and you had to draw this graph, calculate the gradient, calculate the threshold frequency, calculate the work function, and so on. So please bring a ruler and pencil to the exam in case you're asked to do this again. Remember, if the question then says, calculate the value for Planck's constant, you have to calculate it from the gradient of the graph, and you're quite welcome to show it here. You don't see that, but I've actually drawn these lines here to show how I'm calculating the gradient. Show that working clearly. So if you make a little error in here, at least you've shown the working, and people will be sympathetic to you. If you don't show the working, you're not going to get a lot of sympathy. Okay? Show your working. Sometimes it says that. You must show your working. If it doesn't, please show your working anyway. All right? Things like this. Reduced intensity, what happens? Reduce the intensity, you get that. Please don't draw this graph extending flat towards a negative voltage. That's just plain wrong. Question. They observed that the photocurrent is 0 and remains 0. Doesn't matter how much positive voltage you apply. If the frequency falls below the threshold frequency, you aren't going to get a result. Why? Below the threshold frequency, the light doesn't have enough energy to excite the electron to the conduction band. To eject the electron, just not going to happen. Okay, so that's how you can answer that. And more questions on that, please bring a pencil or a nice pen to draw these sorts of diagrams. Okay. Oh yeah. This is from 2017 exam paper. Another question which talks about not explained. Does not support, rather than says it supports. There are quite a few things you can build your answer around. I was telling the previous talk we had that you could put up 3 columns here and talk about the evidences and how they support or not support wave-like and particle-like nature. But you've got to explain why it does not support the wave-like nature. We talk about time delay. If light was a wave, then given enough time, light of lower frequency can eject an electron, but it does not. See, it does not support. The word not has to be mentioned in your answer. Intensity. Increase the intensity. If light was a wave, a more intense light wave has more energy, which means it should be a bigger stopping voltage, but it does not. Right? That sort of an answer has to be brought up. Okay, I think I've already answered these questions about diffraction patterns and the comparison between X-rays and electron beams. Okay? The wavelength is the same, momentum is the same, energy is not the same. They're completely unrelated. Okay? And I think that's what all these questions are about. This was 2011 physics exam paper. Gives you the wavelength of an X-ray as 0.2 nanometers. So let's build our question around that. So if you're given the wavelength of the X-rays, you're given that quantity. So you can work out, say, look, the wavelength of the electron must be the same, right here. So therefore, what must be the momentum of the electron beam? Or given the wavelength, what must be the energy of the electron beam? And you can work all that out. So you can also write this in terms of kinetic energy. And you can work out the kinetic energy of the electron beam. It's going to be very different than h times f of the photon. I think this is a good question, and it takes a little while to get used to it. So I would suggest you at least redo this question when you get home. Here's a diffraction pattern, very similar to, well, it is from VCE. This is 2011 exam paper. And it says calculate the path difference S2P to S1P. S2P to S1P, you've got to count it. P is the second dark band. So it's, the path difference will be 1.5 wavelengths. 1.5 wavelengths. And you can work out the rest from here, what the wavelength of the light beam would be. Okay? And then you have the fringe spacing equation to work out the rest. So those concepts are really important. The units are important. Don't forget converting nanometers to meters. Similarly, same question here. I've left these here for you to explore at home. I didn't intend to do all of them here. Okay? We would need at least another couple of hours if you went through all of them. And again, this is a description that I have been talking about, that electrons can diffract. Electrons can diffract means they can have wave-like properties under certain conditions. You don't say electrons are waves. They're not. But they can take on wave-like properties. Light can have momentum. It does have momentum. Right. This is from a previous exam, VCE exam as well, and it shows the electron gun. Once again, you must show your working, ask you to calculate the de Broglie wavelength as h over mv. The reason I put that there is to show to you that you can get the de Broglie wave at 10 to the minus 11. 10 to the minus 11 is slightly smaller than the interatomic distances. If you use this as a diffraction, to get diffraction patterns, what you will get is a diffraction pattern which shows a few dots up there. So the rings are there, but a little bit dotted. That dotted is more characteristic of an electron beam. So somewhere here I had a comparison of X-ray and electron beams. Can you see these dots here? In my own research, I've often seen those dots coming from electron diffraction patterns because they have a slightly lesser wavelength, so better resolution. The d-spacing won't change, but you'll see more dots rather than fuzzy. Now, what is today's quantum picture of an electron? What you learned, and this related to what I'm talking about here. So this whole idea of here's the nucleus, and around that you have got these electrons buzzing around. It's all outdated and gone. You know that by now. At the very least, we talk about leptons and quarks, not electrons, protons, neutrons. It's an outdated concept. But what does it mean? The electron doesn't reside in a circle like that. The electron can reside anywhere here. So that whole area is a probability density map where the electron can reside. Okay? Yes, the highest probability could be around here, but the electron could be anywhere else as well. And that's to do with Heisenberg's principle as well. All right, so going back to where we were, over here. Right. Would you see an electron diffraction pattern? Now, if you have a look at this, this is slightly smaller than the interatomic distances. And what do we say here? If it is much less, then you won't see diffraction. But if it is slightly less, you will see diffraction. So the VCEE answer was that no diffraction would be seen because the distance of the gap is 0.5 millimeters. They exaggerated that gap to ridiculous values. If you look at any crystal, the interatomic distances are likely to be about 10 to the minus 10, maybe 10 to the minus 9 in some crystals, but not much less than that. Magnesium oxide, for example, is 0.42 nanometers. So you're going to see that sort of distances. Okay, not 0.5 nanometers. You're looking at 6 orders of magnitude difference. You're not going to see any diffraction. Okay? When you're looking at spectroscopy results or analysis, please draw these lines. Don't be shy of doing that. So if it says, what are the wavelengths emitted when it drops from 3 to 1, draw those transitions, write out the energies, and convert it to wavelengths. Follow the process, you won't go wrong. Okay? As in any engineering, any science, process is as important as the answer. I think all this is pretty clear. Answering the negative. Yes, we have talked about that. Why does the photoelectric effect not support the wave-like? Why do spectral lines not support the particle-like nature of electrons? How do you answer them? Okay, you have to talk very clearly about why does it not support it, rather than stating why it supports some other theory. We're not asking that. We're asking why does it not support this nature. So when we say spectral lines do not support the particle-like nature of electrons, well, if electrons were particles, then they would exist everywhere. Well, they do in some way. I mean, Heisenberg's principle says that it could be in all sorts of locations. But we're talking about discrete energy levels in the case of the Bohr model, and those would not exist if electrons were just particles. They never had wave-like properties. Okay, that's the important part. Just a little change of scene here. The scientific method and questions on that are also part of your Unit 4. So things like, what's the difference between accuracy and precision? What's the difference there?
Accuracy is treating the instrument being like, whether it's like well calibrated or not. It's like if like a ruler's
Yeah.
it's consistent, but it's just consistently wrong.
So your spread of data is very little.
Yeah, well precision is like the increments on the
Correct. It's the least count of the instrument. Yeah. So if you're talking about how precisely can you measure that distance, that depends whether you use a ruler that's graduated in centimeters or millimeters or micrometers or what. That's how precisely you can measure it. Yeah? But accuracy you would have to do with, you take the instrument away, bring it back, measure it again, take it away, bring it back, measure it again. Are you getting the same reading all the time? If different people come in to get the same reading all the time? So that's to do with uncertainty. So precision and accuracy are two different things. How about these bars that you put here? How do you determine uncertainties from given data? So we have done this in class because we've got a lot of students who are doing music, so I just time it. I say time this, and everybody does that, and we get slight variation. You take the average of that, it's pretty close, but then you take the range. What was the smallest, what was the largest, divide that by 2, there's your error bar. That's your uncertainty bar. Not your error bar, it's an uncertainty bar. Okay? And you can determine that very quickly from data as a range over 2. If you have a graph that you've drawn, you're trying to get the gradient of that, you've done all this in your APIs, haven't you? So you get the gradient of the average, plus minus, highest gradient minus lowest gradient over 2. That gives you a range value. Okay? If you have something like a derived uncertainty, so you're looking at, say, density is equal to mass over volume, then the uncertainty in density will be the uncertainty in mass plus the uncertainty in volume. You always add uncertainties, you never divide, multiply, or subtract. Hang on, they're different quantities. How can you add them? So you take a fraction. Delta M over M plus 3 times delta L over L. Volume, 3 dimensions. Okay? And that allows you to calculate the overall uncertainty in your density measurement. That's called a derived value. I'm sure you've applied that to your APIs already. Huh? So these are the concepts, as I was telling you earlier at the start, that your revision of Unit 4 could be broken up into these topics. Wave-like properties of light. Does that make sense now? A equal to HF is hc over lambda, diffraction, Young's double-slit experiment, they're all wave-like properties of light. Particle-like properties of light, momentum is h over lambda. How did that arrive? I think I showed you somewhere, didn't I? Yeah. So h over lambda, where is that used? Spectroscopy, photoelectric effect. Wave-like properties of particles, electron diffraction, de Broglie wavelength, those concepts. Particle-like properties of particles, electrons can be accelerated. Change in kinetic energy is Q times V. So you can accelerate an electron, gain that much energy. Then you can slam it into a hard, like a tungsten electrode, and get X-rays from it. All that stuff is later. And then evidence versus theories. Bohr model was fantastic. It proved spectroscopy. It proved what we were seeing with the hydrogen spectrum in the light from the sun. Fantastic. Didn't prove anything else. And it was the work of Schrödinger and Dirac and Pauli and Heisenberg that took the steps further, okay? What a time to live in. And somebody spotted that in the last talk. I remember a photograph we have in our office of a conference in Belgium where all these people were together. And these were the people together. I'll show you. There's the list. In that photograph, they had Planck, Philipp Lenard, Einstein, Bohr, de Broglie, Heisenberg, Schrödinger, and Einstein, amongst a few others. You know, they were all in the same photograph. Anyway, I think that was a pretty special time. No calculators, no computers, nothing like that. People still did all that work. So what is the evidence that light can behave as a particle, light can behave as a wave, electrons, etc.? I think we have talked about that today, and you should be able to answer those questions. Basic principles, I think we have covered all that. I don't know what happened here. That should be lambda. I'll change that later. Why don't we see our diffraction pattern? I think we've talked about that. We should have a larger wavelength. We've talked about that. Okay. Higher energy of an electron. We look back at that equation. High energy means lower wavelength. All right. We talked about this in Unit 3 as well. You may encounter in the final exam a question or two that you have no idea what to do with. You could even have that next year. Anybody doing enhancement or uni courses here? Right, they have this thing called a Fermi question. We do that in the 11 Physics Olympiad program. We give a Fermi problem, which means no value is given, and you have to just approximate. One of the questions I gave was, What should be the speed of an asteroid to melt all the ice on Earth? What should be the speed of an asteroid to melt all the ice on Earth? No quantity is given. No mass of Earth, no mass of asteroid, nothing. And I looked at the range of values the class got by taking different values, and the range is very small. That's the Fermi problem. Okay? So why am I telling you that? You could come across a question that you've never seen before, and you don't know where to begin. What do you do? Okay, thankfully this is VCE. You should be able to identify the concept behind that question. For example, is it Lenz's law? Are they talking about AC generation? If they are, what quantities are given? What do I know about those quantities? What do I need to find out? And once you start putting that down on paper and have a sequence that you're writing down, you probably have answered the question. All right? There's no question there that people of your caliber can't answer. I tell my class this, I say you're walking in on 100%, you're walking out minus the errors you made. I think that's where you are. Yeah? We already talked about this. What do you do from here? Summarize your concepts. 1A3 sheet is advisable, double-sided. You can write on them laws, equations, diagrams, whatever helps you understand things. Put some exemplar questions in there, perhaps some worded responses. Get on with, you should have already finished problems from your textbook. It's too late if you're thinking of starting that. It's time to move on to trial points, trial papers, checkpoints, possibly VCAA papers. That's my favorite. I think those papers have been vetted, they're good, they're sensible, and that's the people you're applying for a job with, you know. You should know what they're about. Basically, that's what it comes down to. Time yourself. Not a good idea to do these papers in little chunks at this stage. Sit for 2.5 hours and do a whole VCE paper. Maybe take 3 hours, but no coffee. Yeah, no sugary drinks, no music. Just replicate what the exam environment is like. Now you don't have to put your school uniform, but I think you can do the rest. Just sit there and get on with it. Here's a little timeline that continues. I do invite you to look up where we are today. That's 1927, and I've stopped there. But not a lot happened from 1927 to 2017 in the world of quantum physics. Imagine that big gap, right? And it's maybe just a coincidence. It's about 1928 that the world's first computer was thought of. But anyway, electron diffraction was purely an error. It wasn't supposed to happen. Rutherford's experiment was also a little bit of an error, but we can take credit for that. He was somehow Australian. But what's happening right now? Where are we today with this? Not in your VCE course, but I think it's fascinating. Surely you'd like to know that. So if you have time today, Google in high temperature superconductors nanotubes. And those nanotubes are extremely tiny, and they're being embedded in the CERN detector to see if the magnetic fields can be trapped around it, get lots of data, terabytes of data, and then find the least common denominator to work out a quantum magnetic dipole. Okay? That's an exciting area of research happening right now. Anything else? I think we have got 7 minutes for any questions, or you'll have to go early to English. Take your pick. Now, I'll be here for a few minutes more if you have any questions.